Hi everyone. Thank you for coming or watching this online. So I'm right now probably, I don't know, having a baby or have recently had a baby. So let's do this class. This is the pre-recorded version. So last time we talked about stress, and mostly we talked about tensile stress and compressive stress. And those are like a little easier. They're kind of stresses that are um, directly straight on to the direction the stress is pulling. We're not really worried about stuff going sideways or transverse to the direction of stress. So now let's like kind of start talking about some inhomogeneities. Inhomogeneities is what I'm trying to say. So let me clear up a thing from last time though. Like our stresses aren't exactly uniform, and we kind of approximate them that way. We kind of it's usually like reasonable-ish to say that over the area that we're concerned about, the stress is reasonably uniform, and it's not like totally true. But if we want to get really specific about it, I know last time I came out as kind of anti-calculus. I mean, I'm not, but let's avoid using it when we can. Um, the If we really want to, if we have kind of an inhomogeneous stress, we can integrate it over the area. And, we do that by kind of like taking, an infinitely small area of stress and take the limit as the area approaches zero. And the summation of the sum of stresses across our area of interest uh, is the actual stress. And you can see there's different distributions, and that can depend on a lot of factors. But it's usually like kind of reasonable to approximate it as just sort of uniform over the gauge area that we're concerned about. Um, so that's when we have kind of like concentric loading too. So when we have eccentric loading, that's another story. Like we can see here in figure 1.13, if a force is eccentrically loaded, the stress distribution is going to not be completely uniform, and there's going to be a moment. And we talked about like kind of the moment of inertia in our previous lecture. So we do need to like consider that like a moment of inertia, a rotational force, when we're talking about and not an eccentrically loaded member. So we're not going to really cover that too much. I'm just going to like throw it out there that this is a thing that we need to consider if we do have a concentrically loaded, or pardon me, an eccentrically loaded member. But anyway, let's now move on to the topic of the day, and that's shearing stress. So take a look here at figure 1.14. And what you're seeing here is a force P and a force P prime applied transversely to member AB, and that creates a shearing stress here along plane C, where one direction is opposing the other direction, and that is a shear stress. So they, I guess I already explained this stuff here, and the corresponding shear the shear stress we describe as tau, and that's it's very similar to the formula that we use for your tensile stress. It's your force, your total force over the area of the shearing, and the distribution varies from 0 at the member surfaces. And let's see, it's not uniform is what I want to say here. But we're going to kind of approximate it as uniform, just because it's like a little much to not approximate it as uniform. So here's some examples. A lot of the time when we're talking about shearing stress, we are talking about bolts. So take a look at figure 1.16. We've got a couple members joined together by a bolt, and this is a single shear here, in that there's one plane. The plane between A and B is the kind of the spot where we get our shearing stress, and that's where we're concerned about. And there's also a double shear. So take a look here. We've got member A, member B, and then bolts EG and HJ. And the difference here is, take a look at force F. If we, in the double shear situation, we've got two surfaces. So the force F is kind of split over two shearing surfaces between CA and DA. So that's really our main difference. And these are the two that tend to come up a lot right here. And another sort of shearing stress we're going to worry about too is your bearing stress. So that's when you've got a bolt, it's sitting in a socket like this, or with a diameter D, and the resulting force is on the surface is equal and opposite, excuse me, to the force exerted on the pin. And this is covered up a little bit, but your bearing stress is equal to your total force over your area. So what's kind of interesting to me always too, I remember when I was sort of first tempted to look at a surface like this, I'd see the surface of the bearing, and I'd want to say to myself, well, that's we'd have to do the force over the whole area, but that's not actually how it works. When you've got a force like kind of a semicircle like that, the force is still always pointing directly in this direction. You know, it's from the bolt. The bolt also has a semicircular area, well, you do have a larger area if being a semicircle as opposed to just a flat surface. Because the force is not direct on, it kind of like cancels itself out a little bit. So basically having a flat surface and a semicircular surface like that are pretty much the same. So we're really only worried about the diameter and the thickness. That's how we're going to determine the total area. I think that's what's covering up right here. The area here is diameter times the thickness. The diameter of the semicircle times the thickness of the member. So that's going to be P over dt. Okay, so let's do an example on using the previous situation that we had before. We have this this boom, and we have a horizontal member. And now let's talk about the thicknesses a little bit. This boom, or pardon me, the horizontal member on the bottom is 50 millimeters in height, 30 millimeters in thickness, and we have these this clevis that's attaching it to the wall. That's 25 millimeters in thickness on each side, and we've got a pin that's 25 millimeters in diameter. We're kind of like adding complexity to the previous problem. It joins up there when it's hitting the wall, and then here at B, it's now kind of splits into a fork and joins up there with a thickness of 20 millimeters on each side. The center bit of this is what attaches to the boom. That's CB, and that's a circular, as we recall from previous, I'm sure you remember yesterday, that was 20 millimeters in diameter. At the top, it connects here. We've got a pin with a 20 millimeter clevis. I don't know if that's a clevis, if it's only one side. I've only used the word clevis for two, but I'm going to use it here. We're going to call it a single clevis. 20 millimeters. It's a 25 millimeter diameter pin holding them together. And then when it joins here together at B, we've got again the same 25 millimeter pin. And now we've got a complex little joint. So here in the center, this is the top, the rod, the boom, if you want. Outside of that is the fork here, joining from the horizontal member. I guess that's the boom. I've been calling the top the boom, whichever, the horizontal bit. And then on the sides of that, outside of that, remember, that's what's holding the bit that's hanging, the 30 kilonewton load that's hanging down below that, all joined together by a pin 25 millimeters in diameter. That's a lot of complexity right there. Good thing we're doing this like it's recorded. You can pause this and look at it a little bit. This is also in your book. So stay with me, y'all. Now, from a statics analysis, remember the force on AB was 40 kilonewtons, and that's in compression, y'all. We're going, sorry, it's a mirror image. We're going that way. This boom is in compression, whereas the top bit here, it's in tension, and that is 50 kilonewtons. So we got 30 kilonewtons hanging, 40 kilonewtons of compression here on the horizontal member, and the diagonal rod, 50 kilonewtons of tension. Here, I'm going to put my face away so you can read this. I just figured out how to do that. You've got to consider the maximum normal stresses in A and B and B and C, and the shearing stress and bearing stress at each pin connection. So here's what we're worried about, y'all. We want to figure out sort of like where's the weakest point to. That's what's going to fail. So let's look at the rod. Now we're at the top of that triangle. I'm going to put my face back. At the rod's center, the average normal stress in the circular cross section is 159 megapascals. And we decided that last class on Monday, right? That's just like the force over this circular cross section in the member that's in tension, the horizontal member, right? The rod. Now, at the flattened rod ends, and we're talking about here on the end bit, right? There's the hole, that's the stress on the pin, but the thing on the sides of that, that's actually the smallest cross-sectional area. So that's what's going to fail first. That's what has the least area. So let's figure out what that is. Area of 20 millimeters times 40 millimeters minus 25 millimeters. So the 20 comes from, that's area here, 40 millimeters. And I should say that's the area of this like clevis, the single clevis that's coming out of the wall. 20 millimeters, that's the thickness. 40 millimeters minus 25 millimeters, that's the thickness, the total thickness of this kind of the end piece right there, less the 20 millimeter center bit, that's the size of the hole. So it's a 15 millimeters in thickness total, 20 millimeters hole. So the actual area is 300 millimeters squared. So your stress now is the total force, which we already figured out, over 300 millimeters squared. You get 167 megapascals. So that's your stress on your end member at the weakest point. Now, remember that number, 167 megapascals. I assure you that that is going to be the highest stress we're going to encounter. I know I kind of already told you the answer. Maybe if I wanted to be like a little more sly about this, we would have like looked at all the parts first and then figured out like which had the most stress, but this is the way I'm doing it. I'm just telling you that's the answer. But let's look at the other areas, and we'll see that they have like less stress on them. So the boom is in compression with an axial force of 40 kilonewtons and an average normal stress of minus 26.7 megapascals. I'm going to put my face away. The sections of minimum area at A and B are not under stress since the boom is in compression and therefore pushes on the pins. So remember, that's the boom, that's the horizontal member we're talking about. So I just wanted to like kind of make that clear that we're not worried about the side bits here for the horizontal member because the boom is pushing directly on the pin. So we're really only worried about the bearing stress there. Let me repeat that again because I remember when I reviewed this myself, I confused myself. We just calculated, we figured out this little area here and this plus this little area here and decided that's the weakest part of this and that's what's going to fail first. And I'm telling you that we didn't worry about that for the horizontal member because when this is in compression, let's go back and like look at that. I I can't actually go back when I'm recording slides, so I'm sorry. We're just gonna have to visualize. You can record when you're looking at the slides. Go back and look at the whole structure. When you look at the horizontal member, when boom AB is pushing on there, that these bits right here on the side of the pin, they don't come into play at all. We don't worry about them when it's in compression, just because the member itself is pushing directly on the pin, so that's all we got to worry about. We only worry about these area when we're in tension, like we are in BC. Okay. So let's talk about the pin shearing stress, because that's what we're here for. That's what this lecture today is about, is the pin shearing stress. So remember I mentioned this is a single shear. This is the pin up at C on the top. We've got a force going one way and we've got a force one way. Now remember from our previous, this is the thing we figured out during our first lecture. We've got a total force along the top rod of 50 kilonewtons. Yes. Sorry, I've got a mirror image when I'm looking at myself. Along this rod, 50 kilonewtons pulling on the top pin here, pin C. So we want to figure out what is the shear stress. So what's the area of that pin? Pi r squared, and it's 25 millimeters over 2. It's 25 millimeter diameter, so 12 and a half is your radius times pi. We get 491 square millimeters is your area of the pin. So the force on the pin is equal to the force exerted by the rod BC. That hopefully that makes sense. It's just because the total force pulling on that rod, it all goes into the shear. It's all there. So your shear stress is your total force over the area we just calculated. So 50 kilonewtons over 491 millimeters squared, we get 102 megapascals. So as I mentioned before, less than we were finding pulled on the sides of that end member. So this is not what's going to fail first, but we're calculating that. We're figuring out that thing that I already told you is right. And the force at A, or pardon me, the pin at A is in double shear. Now we're on to pin A. So this is right here. Now this is at the bottom, recall. Remember, we've got 2 of them anchored into the wall. Pin A is in double shear, so there are 2 areas that it's pulling on. And recall, we're in compression on the bottom. Your bottom member has a force of 40 kilonewtons in compression in a double shear. We've got this sort of double clevis here, and here's our pin A. So how do we calculate that? The difference is we just take our total force and we split it in 2 because it's on 2 surfaces. It's divided by 2. So 20 kilonewtons on top divided by our total area. Same total area as on the top because it's the same size pin. So we've only got 40 megapascals on the bottom. That's not what's failing first either. So even less. And you can see we've got less force. And in the double shear, we've got less force on each particular surface. So, I mean, that's kind of like if you're building a structure, that's a better way to go. Okay, let's talk about now pin B. And pin B is a little more complicated than our others. So I want you to refer back to the slide that showed the whole thing, just to be able to sort of see this a little better. And I think, like I mentioned in the previous slide, I can't go back when I'm recording a slideshow. So, if you're watching at home, pause and go back and look at the whole structure. Or Evelyn, go back a few slides to where we can see the whole structure in class. And let's take a look at that for a sec, put it in context. So here it is without my face. And so let's examine pin B. So in the center here, this is the end of the boom AB, the vertical one with a load of 50 kilonewtons. And here on either side of that, that is the double clevis coming from the horizontal member BC. and that had a total compressive force of 40 kilonewtons. And on the outside of that, this double clevis hanging down has a load of 30 kilonewtons, and that is the hanging load at the end of the boom. So it's a little complex, so let's go through this bit by bit. We're interested in sort of figuring out what's the force at every spot on this pin. So we can think of the largest force is at G, so that's 25 kilonewtons. And you might say, Dr. Raymond, this was just a single boom, and you said it was 50 kilonewtons on that. So, but remember, it's a double shear still, because we have, well, it's just a single sort of member right there. It's got a double clevis on either side of it. There's still two shear surfaces right there. So we actually are under, you know, a shear force. So we are actually worried about, we will regard this as a double shear. So our 50 kilonewtons of force on the vertical rod, we do divide by 2 and get 25 kilonewtons. And that's our largest force on this pin. And we can look at the average shearing stress. It's, you know, at any point, 25 kilonewtons divided by our area, and we get still the maximum shearing stress right there is 50.9 megapascals, still less than what we had up top on our clevis at the top of the vertical boom. So this is not going to fail first. So still not all that worried about it. Okay, let's talk about pin shearing stress. So now we're down on the part where the bottom, the horizontal member attaches to the wall. And we want to determine the bearing stress on A in the boom AB, where we have a thickness of 30 millimeters. Remember, this is like a rectangular member, a rectangular horizontal member, and the clevis on either side is 25 millimeters. And the diameter of our pin is 25 millimeters. So recall, our bearing stress is our total force over thickness times diameter. Your thickness, 30 millimeters times the diameter of the pin, 25 millimeters, 53.3 megapascals. Like I mentioned before, not what's going to fail first, but that's how much stress is on it. And determine the bearing stress in the bracket as well. Similar calculation, but instead we're going to use 50 millimeters as our area. But, you know, pretty similar. Similar calculation, and we get 32 megapascals. So we're cool. Not what's going to fail first. Okay, we're pretty much at the close of our lecture. It's a shortened lecture. I'm having a baby tomorrow, so a little shorter today, but we're going to make up for it with a lot of stuff on Friday. So let's talk a little bit about what we're going to talk about. We're going to talk about a little bit more stress on Friday, but also we're going to start analyzing our real-world problem, and that is this reactor pressure vessel that I'm very interested in. So let's do a little drawing, and I'll preview what the problem that we're going to be solving. So this reactor pressure vessel kind of looks like this. You got a big cylinder, and now there's a head on it. Okay, there's also a head on the bottom, but we're not worried about that one. Let's just talk about this head. Now let's zoom into that a little bit more. Look around here. Do you see that? See all those like little spots where we could have bolts in there? That's what we're going to do. We're going to attach this head to the body of the pressure vessel, and there's going to be a lot of bolts in there. And each of those bolts is going to have a particular diameter, and we need a certain number of bolts, and there's going to be a particular pressure inside this pressure vessel that those bolts are going to need to resist. So let's get thinking about that problem a little bit. like, what's going to happen? The pressures that are exerted upward, and I alluded to this earlier in the lecture, so you can go back and watch it if you feel like it. Um, when we have a circular surface, you might think to yourself, do we use the total area in figuring out the stress? We don't. It's just the stress pointing straight up. So we're going to analyze the stress that's on this, and we're going to decide like what bolts we're going to need to use to keep the pressure vessel head on the body of the pressure vessel in this situation. This is like kind of a real world engineering problem. It's a little bit simplified, but it's the kind of thing we need to think about as nuclear materials engineers. And we're going to like be revisiting this problem a lot over the course of the bad choice of words. As we go along, we're going to add complexity to this, but we're going to start off just looking at this very simply and kind of decide what size bolts and how many of them we need to hold the pressure vessel head onto the pressure vessel body. So we'll do that next week, and we'll go from there. We'll add complexity. So we'll see you all Friday, and be well.